Hello everyone, this will be lecture number 6 of solid mechanics. In this lecture we have two small chapters. The first one will be about plane stress and the plane strain, and the chapter 2 will be about field criteria. So we have two small chapters, we will do them in one lecture. We'll start with the first part of the lecture will be about the plane stress and the plane strain. In this chapter at the beginning we just do a small review about what we had before in the course until now. Then we continue to start with these two concepts. So the first point that we did, we defined what we call the stress tensor. So we have three normal stresses and different shear stresses. Also, we defined what we call the strain tensor. We have the normal strains and the shear strains. And with that, we said that the relation between the stress tensor and the strain tensor, or between the stress and the strain, depends on the material properties. So depending on the material that we have, we'll have a relation between the stress and the strain. And depending on the type of the material properties, the relation between the stress and strain will be different. In particular, we said that for elastic materials, we will have a direct relation between the stress and the strain. And also, if you don't have any stress, you don't have any force applied, so the stress here is related to the force over the area, while the strain is the intensity of deformation. So how much we have deformation over the initial length. That's the basic definition of strain. So the stress, if I don't have any strain, I will not have any stress. If I don't have any stress, I will not have any strain. And there will be a direct relation between the stress and strain for elastic materials. Also, more particularly, we said for linear elastic materials, so when we have linear elastic materials, the relation between the stress and the strain will be linear. So if we take the stress tensor and the strain tensor, any stress element that we take here from the tensor, we'll have a linear relation with all the strains. For example, the first stress here will have a linear relation with all the strains, the second stress here, and so on. So this linear relation between the stress tensor and the strain tensor can be written on the matrix form. So the stress is the matrix, we call it C here, a constant of constants, a matrix of constants times, or the product between C and the strain. So see, as we can see, we have a lot of variables here. Here in the stress tensor, we have 6 variables, 3 normal stresses and 3 shear stresses. And the same for the strain, we have 6 variables, 3 normal strains and 3 shear strains. And as we said, always the strain tensor and the stress tensor, both of them are symmetric tensors. So here always that tau 1 2 will be equal to tau 2 1, and here epsilon 1 2 will be epsilon 2 1. So that's why we say only have 6 variables, not 9. So this is only for linear elastic materials. Now, as we said also, if we have for linear elastic material, we define the material properties, the modulus of elasticity we call it E, and the Poisson ratio we call it nu. And we said if I have the stress, the normal stresses sigma x, sigma y, sigma z, here if I am in an xyz reference system, if I have this normal stresses sigma x, sigma y, and sigma z, we can find always epsilon x, epsilon y, epsilon z. So we can find the normal strain if I have the normal stresses. Also, in the same way, if I have the shear stresses, I can find the shear strain. So to find the shear strain, it will be direct relation. We said we have here G is the shear modulus, which is the equivalent of E, but for shear. So E is the modulus of elasticity for normal strains, and the Poisson ratio, as we said, minus. We put the minus here to show that even if I have a stress in the y direction, I will have a strain in the x direction, but minus. If I do a tension in one direction, I will have a compression in the lateral direction. So that's what we said also previously in the previous lecture. And we said that we have a relation between the modulus of elasticity E, the Poisson ratio nu, and the shear modulus G. So we can, if I have only two properties, I can find the third one. So if I want to write the strain as a function of the stress, just by developing these relations here, so 1 plus nu over E, it's 1 over 2g, so I can find each strain as function of each stress. Okay, so here we use 1 2 3 4 5 6, or we can use x y z. Okay, so these are only the just symbols here, 1 2 or x y, so it's the same. So the idea here for linear elastic material, if I have the stress, I can find the strain. Now if I take these equations as they are like here, and then I try to find the stresses as function of the strain. So we have three unknowns, three equations, three unknowns, so I can do some rearrangement. And we can find finally also, I can write the stresses as function of the strain. Now if we do the arrangement here, we define what we call the Lamy constant, so lambda here. So also as function of E and nu, so we can find also a relation. If I have the strains, I can find the stresses. Now for us, we don't need to memorize everything here. We just need to know that if I have the strain, also we can find the stress, and also I will have a linear relation. So this is also only valid for a linear elastic material. So here we call what we call the elastic problem. So the general formulation for if I have a body, we have a force is acting on an object, on a solid object or a solid body, and what we need to solve in solid mechanics. So that's what the objective of solid mechanics. We need to find all the components of the strain tensor at a point. So we need to define a point on the object. We need to find the strain tensor. We need to find the stress tensor. And also we need to find the displacement field. So displacement we said is related to the deformation. The point when if I have a point, initial position of a point, I need to check what will be the point after deformation. So all these components we already studied, and we find the relation between stress and strain, and also we know the relation between the strain and the displacement field. So in total we have 6 components in the strain tensor, we have 6 components in the stress tensor, and we have 3 components of the displacement field, so ux, uy, uz. So in total we'll have 15 unknowns that we need to solve. So in order to solve at a point, we need to solve 15 to find 15 unknowns. So for that we need 15 equations. Now these equations are also, we can find them. So we have a relation between the strain and the displacement. We can find them. We know if I have the displacement field using the derivative, the partial derivative, we can find the strain. So the constitutive equations, well, that's what we just discussed in the previous slide. If I have the strain, if I have the stresses, I can find the strain. And also if I have the strain, so these two are the same. I have a relation between the stresses and the strain. And here's the internal equilibrium equation, which means that if I take a cut at any part of the object, I can find a equilibrium. So the sum of forces, here we use the body force if I have weight also included. So sum of forces here, the forces are represented by the stresses, will give me equal to 0. So what we need to understand from this, that yes, indeed we have 15 equations to find our 15 unknowns. But even if I have 15 equations and 15 unknowns, that does not mean that I need to go and solve 15 equations, because this will be too long and too difficult to do analytically, to do it on the paper. After that, we see later that we can do that on a computer using different softwares, using finite element. But for us to do it now analytically, it will be difficult. It will not be practical to solve 15 equations in order to find 15 unknowns. So what we do here, for us, for the solid mechanics, what we do is that if I need to work in 3D, I will have 15 equations and 15 unknowns. So the idea is that we can find different cases in which we can simplify the 3D case where I have 15 unknowns or 15 equations into a 2D case. So instead of having 15 equations to solve, we will reduce substantially the number of equations that we need to solve. So here we define what we call plane elasticity. So when we say elastic problem, we need to find 15 unknowns. This will be in 3D. We call what we call plane elasticity, it will be in 2D. And here we define 2 different types of plane elasticity. The first part is what we call plane stress, and the second is plane strain. So what does this mean, plane strain and plane stress, and how this can be helpful for us to simplify our problem? So let's see together. So let's define what's plane strain. So plane strain is defined as state of strain. So state of strain, when we define a stress tensor, in which the strains normal to a plane are assumed to be 0. So for example, let's take here, if I have XYZ reference system or reference frame, if I have epsilon z is equal to 0, and all the shear strains are depending on z, so epsilon xz and epsilon yz is equal to 0, in this case we call it a plane strain. So plane strain, so as you can see here, all the z components of the strain, so the epsilon z and the shear strains are equal to 0. So as you can see, instead of having the 6 unknowns, I will have only 3 unknowns. So only 2 normal strains and 1 shear strain. So as you can see here, I have 3D strain state. Here I will have 2D strain state. Okay, but here I have three, all the components will be 0. Now in which case we can, so of course when it's not very simple to go from 3D to D, I need to define some cases, some engineering cases where I can do this simplification. So what we can do, what we know, if I want to do this assumption, I need to have one dimension in the object that I am studying. So as you can see, one dimension should be very large compared to the other two dimensions. For example, here x3 is too large compared to x1 and x2. So the dimension here, the length is too long. So that will be the first assumption. The second assumption, I need to know that all the first forces acting on the object should be only in the direction of x1 and x2. I should not have any force acting in the axis 3 direction. So you see, so along the length I should not have any force. Only in this case I can assume that we have a plane strain condition. So that's what's written here. So one dimension is very large comparison with the other two, and the force acting should be acting on the x1, x2 plane. So I should not have any force acting on the x3 plane. Okay, so in this case, epsilon 3 and the 3 direction will be equal to 0, and all the force acting on the x1 and x2. So I will not have any shear strain in any plane passing by the x3. Now why the strain here will be equal to 0? Because we know even if I don't have any stress in the x3 direction, that does not mean that I don't have any strain. Why does the strain is equal to 0 here? Because if the length is too large, so let's call it L3, the length in the x3 direction. Let's call it L3, this length. Even if I have a small deformation here, when we know that the strain epsilon is not the deformation, it's the intensity of deformation. So we know that epsilon is delta L over L. So even if I have delta L here, delta L over L, because I have a very long dimension in the L3, so the L3 should be very large. So delta L over L will be almost equal to 0 because the initial length, so delta L over the initial length, and the initial length is already very long, so delta L over L will be equal to 0. Okay, for example, here we have two examples that we use in engineering, the tunnels and dams. So we will see now how we can do, but for this slide you need to understand that for thick plates, if the plate is very thick and I don't have any force acting in the direction of the length of the plate, as we can see here, so thick, I have a large thickness and I don't have any force acting along the length, along x3 here. In this case I can go from 3D strain to 2D strain. So let's see, for example, why the tunnel or a dam. For example, as you can see here, if I look at this tunnel here or at this dam, in both cases here we say that we have a plane strain condition. For example, if I look at this dam here, we can see that the length here, the length of the dam is too large compared to the width and to the height. Okay, so in this case, that's the first condition. The length is too large compared to the width and the height, or the width and the height. And at the same time, as you can see, the only force acting on the dam will be the force of water. And as you can see, the force of water will be perpendicular to the length of the dam. So I don't have any force acting in this direction or along the length. I only have forces acting perpendicular to the length. So these two conditions are satisfied. So in this case, we can say that I don't need to study a 3D state of strain. I just can study a 2D state of strain along the width and the height. I don't need to study along the length. Okay. So that's it. That's a practical example in which I don't need to study a 3D strain state. So these two examples, this one tunnel in Istanbul and this one in Yazireta. So these two real life examples here we can see. So this is a direct example about the plane strain. So the last part about the plane strain. So that's what we said. If x3 is infinite, of course, when we say infinite, we don't mean the mathematical infinity because that's not in real life. But when we say infinite, it means that x3 is too large compared to the other two planes. And what we said also, because the length is too large, so delta L over L will be almost equal to 0. So that's why we'll have epsilon 3 is equal to 0. So in order when I write the strain state, I will have all the strains here will be equal to 0. But here we need to pay attention that, as we said, if the strain is equal to 0, the normal strain is equal to 0, the normal size does not need to be equal to 0. because we said there are a linear relation between the stress and the strain. Going back to the linear relation, we can find why if the strain here is equal to 0, the corresponding stress is not necessarily equal to 0. But of course, if the shear strain is equal to 0, the shear stress will be equal to 0, because we know that epsilon xy is equal to tau xy over 2g. So for the shear stresses, that's correct, but for the normal strain and the normal stress, if I have 0 here, I don't need to have 0 here. So that's for a plane strain. Just to summarize, I don't need I can directly put zeros here. I need to have two conditions. The length in the x3 direction should be very large compared to the other two dimensions. And the second condition, I don't need to have any force acting in the x3 direction. So that's for the plane strain. Now for the plane stress. So the plane stress, now instead of talking about strain state, we talk about the stress state. Now we don't talk about the deformation, we talk about the force over the area. So here we have, this is the 3D state of stress, or the stress tensor. We have the normal stresses, we have the shear stresses. That's the normal case. That's a random case. It will be like this. But if there are some conditions, I can get rid of the three terms here. I can put them zeros. Also, instead of working with 3 times the 3 with 9 or with 6 components, as we said, we can work only with the 3. So 2 normal stresses and 1 shear stress. So I only can work on only one plane. I don't need to work in 3D. Now, and under which condition we can do this assumption? Here opposed to the case of plane strain, here I need to have one dimension very small compared to the other two. So I call it a thin plate instead of thick plate. So if this one is very thin, if this dimension is very small compared to the other two, in this case, and I don't have any force, always I don't have any force acting in the x3 direction, in this case, we can assume that I can work in only in this plane. So I can just use the stresses in this plane. I can assume that the stress will be 0 along the plane normal to x3, okay, in the x3 direction. So let's see, for example, here. So that was it. X3 is equal close to 0, and all the forces will be acting along the plane here. So in this case, sigma 3, I don't have any force, so the stress along this part here will be 0, the normal stress. So that's why the normal stress here will be equal to 0. But also, as we said before, if the normal stress is equal to 0, does not mean necessarily that the corresponding normal strain should be also equal to 0. So here, what's a direct example here? A direct example where we can use the assumption, the plane stress, is, for example, the example that we just studied in the previous lecture about the thin vessel. Because we know that in a thin vessel, sigma r is equal to 0, while sigma the tangential, so the radial stress is equal to 0. That's what we studied in the previous lecture. While the tangential stress and the meridian stress or the axial stress are not equal to 0, which means that if I want to study the stress state in the RT x plane and R theta x plane, I will have one stress equal to 0 while the other two will not be equal to 0. In this case, I can directly say that I have a plane stress in the TM or the theta x plane. Okay, so when we say T or theta is the same, and when we say M or X is the same, that's what we said in the previous lecture. So this is a direct example where we can directly assume that we have a plane stress. Now, if you want more information about the plane stress, there's a very good video on this link that we can find on the PDF file of the PDF version of the lecture. So you can visit this link. You have a good animation about the plane stress where you can understand better everything that we just said here with animation, but would be also very useful also if you want to have a better understanding of the plane stress condition. Now, here to summarize, the plane stress and the plane strain both are widely used in engineering. So the plane strain, if I want to go from a 3D strain to a 2D strain, I need to have a very thick plate, and I don't need to have any force along the thickness. For the plane stress, the one that we just studied here, I need to have a thin plate. So I need to have a thin plate, and also I don't need to have any force acting over the thickness. I can go from a 3D state of stress to a 2D state of stress. So by putting 0 all the stresses in the plane normal to the thickness. So that's to summarize. For example, let's look at this example here. Given the following displacement field, we have the displacement field. Find the strain state and draw the corresponding Mohr circle. So we need to find the strain state and we need to draw the corresponding Mohr circle. So this example is a revision of what we had in the previous lecture about the strain state. So we have displacement field. So at any point I can find, if I have any point, if I have the coordinates of any point, I can find what will be the coordinates of the same point after deformation using the displacement field. So the displacement field here. So find the strain state, or we need to find the strain components. So to find the normal strain, we know that, for example, epsilon x is the partial derivative of ux over x, the same for y and for z. So we just do the derivative. And to find the, for example, epsilon xy, we need to take 1 over 2 partial derivative of uy over x and partial derivative of ux with respect to y. So these equations we just already studied in the strain tensor lecture. So should be familiar now. So just if I have the displacement field, I can find the strain tensor. And in this case, using the displacement field here, this displacement field, we can find this is the strain tensor. So we can find that we don't have any strain in the z direction. So the normal strain is 0 and all the shear strains also are equal to 0. So we can see here that we have a plane strain condition. What's plane strain? Because even if in 3D I have all these terms here are 0, so I can just study the 2D case here. I can simplify from the 3D case to a 2D case. So that's what we have here, all these zeros, so we can say that we have a plane strain condition. Now how to build the Mohr circle. So to build the Mohr circle, for example here, if I want to just take the 2D case, I have 60, 20, 20, 30. We know we take a point P 60, 20, a point Q 30 minus 20. Then we draw the circle with having diameter between these 2 points. So I'm just studying 60, 20, 20, 30. I did not pay attention to the zeros here, so I did not take the Z direction into account. I'm just studying the XY plane. So as you can see here, so this circle here will represent any point on the XY plane. So the P and the Q represent the XY. If I want to rotate the XY, let's see, to go from X to X prime and from Y to Y prime, as we can see here. So I want to rotate. So as you can see, the green line here corresponds to the X prime and Y prime. So if I have an angle theta here, I will have an angle 2 theta here. So everything that we learned before about the Mohr circle is still valid, but I need to pay attention that I am working in the XY plane. I did not talk about the Z plane. But you need to pay attention to one point. So what about the 0 here? Do we just forget it? Do we just neglect it? So for now, let's neglect it for now. Then we see later if it will be important or not. So here we're talking about the strain tensor. So the same will be also valid for a stress tensor. So everything we talk in this lecture about the plane strain or about the plane stress will be the same. So this is another example here. Draw the Mohr circle corresponding to the following state of stress at a point P. So we have the stress tensor here. We have 3 normal stresses, and we have only shear stresses in the XY plane. I don't have any shear stresses in the XZ and in the YZ planes. So how do we? So here we don't have a plane stress because I don't have here 0. If we have 0 here, we could have considered it as a plane stress, but I don't have. I have a normal stress here, so this is not a plane stress. I just don't have. So how we'll draw the Mohr circle for a 3D case? So we need to understand that if I have a full 3D tensor, I cannot draw the Mohr circle directly. I need to calculate the principal stresses. So how do we calculate the principal stresses? That means that I need to calculate the eigenvalues of the tensor. So I need to start with calculating the eigenvalues. So we calculate the eigenvalues here. And after we calculate the eigenvalues, we can draw the Mohr circle. That's what we need to understand. For example, if I want to find the eigenvalues of this tensor here, we can find the term 21 minus sigma, 15 minus sigma, 11 minus sigma. Then if we do the calculation, we find the 3 values of the principal stresses. So we know sigma 1 22, sigma 2 is 14, and sigma 3 is 11. So 11 is a principal stress. That should be normal because 11 here we don't have any shear in the Z plane, in the planes, so on the XZ and the YZ. So we know that sigma Z is already a principal stress, because we already, I don't have, because the definition of a principal stress is, or the principal plane is the plane on which I will have only normal stress without any shear stresses, and that's what we already have here. So we know already that 11 is a principal stress, so we can use these two to find the two other principal stresses. Now after that, how we draw the Morse circle? So this is this stress tensor that we have. If I want we want to build the stress tensor in the principal planes, we have 22, 14, 11. These are the three values of the principal stress that we already found, and all the shear stress will be zero, because that's the definition of principal stresses. So how to build the Morse circle in this case? We said after we calculate, so the first step is to calculate the three principal stresses. After that, as always, we build reference a coordinate system, sigma in the horizontal axis and tau in the vertical axis pointing downwards. So that's what we do. Now, as we know, these three principal stresses correspond to shear equal to zero. So shear equal to zero, I am talking about this line. So these 3 points should correspond to this line here. So that's what we did. That's what we do. We start by plotting these 3 points on this axis, because I know that the shear is equal to zero. So the shear is equal to zero will be this line. After that, we build the first circle. So the first circle will be between the first two stresses. The second circle will be between the second two stresses. And then we build a third circle between so sigma 1, sigma 2, a circle between sigma 1 and between sigma 2 and sigma 3, and a circle between sigma 1 and sigma 3. So we have 3 circles here in the 3D case. So this is what we call tricircle of Moore. Instead of having one circle of Moore or more circle, we have tricircle. 1, 2, 3. So that's how we build the Moore circle for 3D case. So we build this one circle, two circles, three circles, but as you can see, we always start by finding the three principal stresses. We need to understand also here that any point here on the red line, or any point on the green line, or any point on the blue zone here, in the blue shaded zone here, will correspond to any reference system. If I do any rotation here, I can find this point either on the red or on the green or on the blue zone here. But for now, we'll not be interested on any 3D case. We'll see later that just particular cases where we can study the rotation. We'll see that during the lecture and during the tutorial and the problems that we solve in the tutorials, how we do the rotation. So that's how we build the 3D Morse circle. Here also we need, just in the case, for example, that we had, we can see that we already had 11 as a principal stress. So here in this case, in this particular case, when we already have a principal stress, we don't need also to calculate the three principal stresses directly. What we can do, we can take these two, because we know 11 is already a principal stress, so we can take these two three elements here, and we'll build the Moore circle for this as a 2D case, like we do always. So we take a point P 21 minus 2.4, a point Q 15 2.4, so as we do always. Then we plot our coordinate system. We draw the PQ. So what we did here, we just drew the Moore circle for the 2D state, like we do always. That's what we used to do before. So that's what we used to do before. So nothing new here. But what we know also, that 11 is a principal stress, which means that if I want, we can directly know that 11 should correspond to this line here. Okay. So after that, we have one principal stress here, we have one here and one here. So also we build a circle between 11 and this principal stress, and then we build a circle between 11 and this principal stress. So this will be the same result that we obtained before. Just here, this slide just to show that if I already have a principal stress, I directly can build the Moore circle for the 2D case here and just add the principal stress on this line. So I can use this method or the method of the previous slide. It will be the same. So now here I already have 11 as a principal stress. If I had any stresses here, so I did not have 0 here, I only have one way to do it. I cannot do it like this. I just need to calculate the principal stresses, then build it like the previous slide. Okay. So now what is the meaning? What is the meaning of the, why do we need to build the Morse circuit in 3D? Now as you can see, as we said, any point on the blue zone here will correspond to a point, to a rotation of the XYZ reference system. So here what we can see, so any point, so if I take a point here outside the Morse circle, it does not interest me because it will be outside. I need to take only the points on the circle which correspond to this stress tensor. So what does this mean? That what will be the maximum normal stress that I can obtain at any point? If I take this point here, will be 11. Any point I take, it will be more than 11. For example, if I take a point here, it will be 14. If I take any point here, it will be less than 22. And the maximum point that I can have a normal stress will be 22, which means that any point, the normal stress will be contained between 11 and 22, which means that the maximum normal stress that I can obtain at the point P will be 22, and the minimum normal stress that I can obtain at the point P will be 11. So that's the first point that we can understand, or we can get from the Morse circle. Also, the second point, we can find that the radius of the circle. So that's how do we calculate the radius here. As you can see, if I take the biggest circle here, so the biggest circle, the radius of the biggest circle, as you can see, the diameter will be between the point 11 and the point 22, the diameter. So to find the radius, I just can subtract 11 from 22, so 22 minus 11. So 22 minus 11 over 2, it will give me the radius. So here we had a small error. So the radius here, so the diameter of the diameter of the diameter of the biggest circle here, so the diameter of the biggest circle will be equal to 22 minus 11. So to find the radius of the biggest circle here, we just divide the diameter by 2, so it will be 1 over 2, 22 minus 11. So the radius of the circle here will be 5.5. So that we can calculate it. So always is 1 over 2 maximum sigma max minus sigma minimum. So it's very clear that because we have the diameter between 11 and 22, so we can find the radius. Now why the radius is important for us? Because as we can see here, as we said, so the normal stress at any point P will be between 11 and 22. Also we can see that any shear stress, this is the zero shear here we said, and I can measure the shear from this point going up or going down. So we can see that this point here, so any shear will be between 0 and this point. So this will be represents the maximum shear if I talk about absolute value, or between this point and this point. So any point P, if I take this point here, this will be the shear. If I take this point, this will be the shear. As you can see, when I go down, the shear will be increasing. Okay, so this will be the maximum shear that I can have. So as you can see, the maximum shear, the value of the maximum shear, as you can see, the value of the maximum shear here is equal to the radius. So the maximum shear stress that I can find at the point P will be equal to 5.5 in this case. So that's why how we can use the Morse circle. So after we build the Morse circle in 3D, we can find the radius and we can find the maximum shear stress that can occur at any point. So that's very important to understand how the maximum shear stress that can occur is equal 1 over 2 sigma max minus sigma minimum. Now here, just before we finish with the 3D Morse circle, also very important point. That's what we said. If you remember the previous examples that we found that we used for the strain tensor, what we said about if when we simplify this model to a 2D strain state, and we said what about the zero? As the zero, how we can we neglect the zero or not? So if we neglect the zero, we can find that I have 60-20. That's what we build. We can build the strain, the Morse circle for the 2D case, but here in this case, this will be the maximum shear strain if I just take the 2D case. But what do we know about the zero here? We can see that the zero here is also a principal stress. So the principal stress, if I want to plot it here, this will be a point here. Zero is a principal is a principal strain because we're talking about the strain tensor here. So zero is a principal strain, so it will be the point will be here. So I need to build also a circle between this point and this point. And also I build a circle. So this is I can build the Morse circle in 3D. So now if I want to find the real shear strain, the maximum shear strain, I will take this point here. So if I just take a 2D case, I will not take into account the real Morse circle. So in order to study the real case, I need to build the 3D state. So that's very important because if I just take the 2D case, I will be underestimating the real maximum shear strain that can occur at the point P, where I am studying the strain state. Okay, so that's very important. So even if I have a 2D case, I need to go back to the 3D case and build the 3D more circuit from now on in order to study the maximum shear strain or the minimum normal stress and so on. Okay, so that's very important just to understand this. Now in the tutorials, we have a detailed problem about the Morse circuit in 3D where we can understand it also better. We can get a deep understanding of it, and also we can do some operations and see how it can be very useful in some applications. So for now, that will be what we need to understand about the 3D Moore circle. So this will be the first part of the lecture. Now for the second part of the lecture, so second part, as we said about the yield criteria, it will be a little bit different from the first part, so they are not closely related, but there is some relation between them. But we need to understand that in the course, these are two different chapters, but are compressed in one lecture. And in the tutorial, we'll have problems about the two at the same time together. So the yield criteria. So now we start a new chapter. And the yield criteria, just to remind what's yielding. So yielding, when we say yielding or plastic deformation, is a type of failure. So failure that should be prevented in the design of engineering components. So if I have a component, if I have a plastic deformation, let's say, so on my original design, my initial design, I should have, for example, here a straight lines, but due to some plastic deformation, it's not straight anymore, so it can affect my whole design. So this is only an element. So yielding, when we say yielding, when we have plastic deformation or a permanent deformation, when the deformation cannot be recovered, so if I remove the load, I don't go back to the initial shape, this is a failure. So this is a failure that we need to prevent. So when I do the design, I need to understand under the loading that I will have, under the force that I will be applying on my design, will it yield or not? If it yields, so it means that I have a problem in my design that I need to prevent. So in this small chapter, we study how we are the criteria that are normally used in order to prevent having this type of failure in my design, in the application of my design. So let's just do a small revision. So normally in a simple tensile test, as you can see, I am applying a force here. Let's call it Px, only in the x direction. That's what we said. We said that for any stress, for the force over the area, I plot the stress, I can find the corresponding strain, which is delta L over L0, and I can plot. And then we said there's a point here I have from which I will start having plastic deformation. So here, if I remove the load, I will go back to the initial shape. While here, at this point here, if I remove the load, I will not go back to the initial shape. So I will have a permanent deformation here. And this is the yield strength. The second point about the yield strength, as you can see above the yield strength, when I exceed the yield strength, even if I increase the stress by a little, the strain will increase by a very large values, as you can see. So any small force will cause a large deformation also. So two different information that I can understand from the yield strength. So the sigma y here, as we said, this property of the material. So each material has its own value of sigma y. We call it yield strength. And in this case, in the case of a simple tensile test, it's very simple. I can say if the stress is above sigma y, I will have a plastic deformation. If the stress is below sigma y, I will not have a plastic deformation. My design is safe. So very simple in the case of a simple tensile test, because in simple tensile test I will have only a stress in the x direction. I don't have any other stress, and you can go back to the tutorial that we solved, the first tutorial that we solved, the first problem of the tutorial that we solved in the behavior of materials tutorial. We find this stress tensor, and we said also, as we can say here, that if the stress here is smaller than sigma or smaller than sigma y, I will not have any failure. So the criterion is very simple here. The stress is above sigma y, above the yield strength, I will not have plastic deformation. Just also to remind you, sigma y, when I say sigma y with a big y like this, it means yield strength or yield stress. It does not mean y direction, the y here. The y here is very different than the y here. This is y here just a symbol to symbolize the word yield, because this is a property of the material. This is a constant for any material. While sigma x here is the force over the area, depend on the force that I am applying on the load. So for the simple tensile test, it's very simple. If the stress that I have is greater than the yield strength, as I have let's say deformation, if it's less, the design is safe. So there's nothing complicated here. But let's say, so this is a simple tensile test, just specimen and tension. I am applying a tension. Now let's say if I have, for example, let's look at this example here. I have this element here. I have a force here, a force here, vertical force, a horizontal force here. I have a torque here. So the stress state here will be very complicated. I don't have only a simple tensile test. So if I take any point in the design here, I will have a very complicated stress tensor. It will not be only sigma x and the other will be 0. I will have a 3D state of stress or 3D state of strain. So how do I cannot say here that if sigma is less than the yield strength, I will not have plastic deformation. Because here I have 9 or 6 different components. Which one I need to choose, I don't know. So I need to define what we call a yield criterion. So yield criterion to know if the stress state can produce plastic deformation. I need a criterion that will allow me to know if I have the stress state at any point, will I have a plastic deformation at this point or not. So how we do that? That's what we study in this chapter. Just also to when we say criterion or criteria, just a reminder, when we say criteria, it's the plural of criterion. So when I say criterion, I'm meaning one criterion. If I talk about more than one, I use the word criteria, just to remind you a simple reminder about English. So the simplest way to define an equivalent stress. So what we can do here, because I don't know what we can do from a 3D state of stress, I need to define an equivalent stress, and then the equivalent stress. So we see how we can define the equivalent stress. We can compare it to the sigma y, the yield strength that we already defined, and we see if I will have plastic deformation or not. So if I have a 3D state of stress, how we can predict if I will have plastic deformation or not? We have a lot of criteria that was proposed previously. So let's go just do historically. The first one was proposed by Rankin and Lamy in very old in 1857. So what they said, what they just said, they said if I have a point, I want to check if at this point I have plastic deformation or not. Just instead of using the stress of state, just calculate the three principal stresses. And if any one of these three principal stresses is greater than the yield strength of the material, I will have plastic deformation. So it's very simple criterion. And the sigma y, as we said, is a property of the material that we can obtain using the simple tensile test. So this is a property of the material. This will be given. So that is what they said. Just find the three principal stresses. If one of them is greater than sigma y, I'll have plastic deformation. So this is the first criterion that was proposed. Another criterion that was proposed by Saint-Venant and Poncelet, also in the 1800s. So he said instead of using the principal, so find the principal stresses, but instead of using the principal stresses, we need to find the principal strains. So we compared here the three principal strains to the strain corresponding to the yield point. And if the strains is greater than the yield strain, we have a plastic deformation. So this is all very similar to the previous one, but here they proposed using the strain instead of the stress. And if I have the stress, we know how to calculate the strain always using the Young's modulus of elasticity and the Poisson ratio. Okay, so this will be the second criterion that was proposed. A third criterion that was proposed by Trami and Hayek, also in the 1800s always. What they said here, instead of using only the principal stresses or only the principal strains, what they said that we compare the energy, the strain energy. Also to remind you, the strain energy at any point here, we said also in a previous lecture, it's defined as the integral of sigma d epsilon. Okay. So here what I said just said that if I find the strain energy corresponding to this principal to the principal stresses, we compare this to the strain energy corresponding to sigma y. So we find it's equal to 1 over 2 sigma y square over e. So that also you can find it in a previous lecture. So the strain energy corresponding to this point is 1 over 2 sigma y square over e, which we call what we call the modulus of resilience. So if this modulus of resilience is smaller than the strain energy corresponding to the principal stresses, we'll have plastic deformation. So this is also a third criterion. We'll see later how we calculate this, but for now just it's based on the strain energy. Now the three criteria that we already studied, The problem with the three criteria that we already I just showed is that when we compare them to the experiments, so to some experiments that we did, we found that they were not able to predict the results, which means that for example, one of the criteria says that we will not have plastic deformation, while in the experiment we already had plastic deformation, which means that the three criteria was not very accurate. Also, another point that we found also in experiments that in the case of hydrostatic pressure, what do you mean by hydrostatic pressure? So if the case we don't have any shear stress, so if I take any material, we just apply forces in all the directions, pressure, let's say pressure in all the directions, in a way that I have a uniform stresses, I don't have any shear stress on any plane. We found that any ductile material will not have any plastic deformation. And when studied, when they, st- when we, when the, some experiments were done on the microscopic mechanism of plastic deformation, so just looking at the structure of the material during the plastic deformation, we found that the yield or the yielding starts and is driven by shearing stresses. So these two, when no shear stresses, we found no plastic deformation. And the microscopic observation showed that the shearing stresses. So when the structure here, we can see that the modification occur by shearing. So only the whole conclusion of all of this was just that yielding is only driven by shearing stresses, that the normal stresses are not very important. So what do you know about the shearing stresses? What is the difference between shearing stress and the normal stress? Shearing stress, as we know, as we can see, it causes what we call distortion, a change of shape. It will cause a change of shape, not only a change of size like the normal stress, a change of shape. So this is what we call distortion. So distortion is responsible for yielding. So what does this mean? So why was this helpful? Because this was helpful because it allowed us to find different criteria based on the shear alone. So let's forget the normal stresses. Let's find a criterion based on shearing alone. So this field led us to the Tresca. So this one criterion was found by Tresca. So what did it say Tresca? Tresca said that if I have this state of stress at any point, at a point, let's say P, if I don't want to understand, if I want to check if I have plastic deformation or not, I need to find the maximum shear stress that can occur at the point P, and then compare to the sigma y. How do we find this shear stress at a point if I have the 3D state? I need to build the 3D more circle like we did before and take the radius. That's what we just saw in the plane stress lecture, plane stress chapter. So how do you find the radius? We said we take sigma 1, let's say sigma max minus sigma mean over 2, that's the radius. So sigma 1 here, if I don't know which one is sigma max and sigma 2. These three are the three principal stresses. I take the three principal stresses and I compare sigma 1 minus sigma 2 over 2. The radius should be greater than sigma y over 2. Sigma 1 minus sigma 3 over 2 should be greater than sigma y over 2. Then I take the third, also sigma 3 minus sigma 2 over 2, and also I take the absolute value because sigma 1 here is always positive. This is the yield strength, is always positive. So that's it. So the first the first point to start with is to find the three principal stresses, just to directly to understand how we use the Tresca criterion. So the first point is to calculate the three principal stresses, sigma 1 or sigma 1, 1. So are just symbols. Uh, if sigma 1, 1 minus sigma